Recently, Google and Samsung launched two breakthroughs that hit the AI world from completely different angles, but with equally disruptive impact. Google's new Ironwood TPU, a seventh-generation accelerator capable of linking over 9,000 chips into a single pod, is pushing cloud-scale computing to limits even Nvidia hasn't reached. At the same time, Samsung unveiled an on-device breakthrough that compresses a 30 billion parameter model, which normally needs more than 16 gigabytes of memory, down to under 3 gigabytes, small enough to run directly on a smartphone. So let's start with Google's Ironwood, the company's brand new 7th generation TPU that has moved from internal testing to full rollout. Its arrival marks the first moment in a decade where Nvidia's grip on AI hardware feels genuinely threatened. For years, TPUs were treated as specialized tools, designed mostly for Google's own workloads, and rarely seen as a direct competitor to Nvidia's most advanced GPUs. But this time is different. Ironwood isn't a quiet internal upgrade. It's a direct hit, landing at a moment when AI demand is exploding, and the companies building the world's most powerful models are searching for alternatives that can break them out of Nvidia's supply-constrained ecosystem. The numbers alone are alarming for Nvidia. Ironwood delivers more than 4 times the speed of Google's previous TPU, and early users are already committing at unprecedented scale. Anthropic didn't just test these chips, they signed up for up to 1 million of them to train and serve Claude. A decision of that size is not made casually. It tells you two things. The performance is real, and the economics are even more compelling. But the real difference begins when you stop comparing individual chips and start looking at how they behave together. Nvidia's biggest architectural move this generation was the NVL72 rack, a system that combines 72 Blackwell GPUs into a single compute domain. It's impressive, and it's a major step up from the old 8 GPU boxes. But when you place that next to what Google is doing with Ironwood, the contrast is almost surreal. Ironwood pods begin at 256 TPUs, and Google's largest configurations reach 9,016 chips in a single pod. And if someone needs more, Google's Jupyter Fabric can chain 43 pods into one massive cluster. That's almost 400,000 accelerators operating in a unified environment. Meanwhile, Nvidia's clusters, as large as they are, rely on layer after layer of packet switches. It works, but it introduces congestion, queuing delays, and scaling inefficiencies the moment workloads start pushing boundaries. So Google took a completely different path years ago and has stayed committed to it. Ironwood continues Google's long-term strategy of using a 3-dimensional torus mesh for communication. Each TPU connects directly to its neighbors, so data moves chip to chip. Instead of being routed through massive switching arrays, this topology reduces power consumption, simplifies communication paths, and produces more predictable performance, especially in workloads that need consistent cross-chip communication. But the part of Google's system that stands out the most is its optical circuit switching layer. This is nothing like the packet switches Nvidia uses. Optical switching works by physically redirecting beams of light using tiny mirrors or MEMS devices. Instead of routing packets, it rewires the cluster itself in real time. It behaves more like a dynamic fiber patch panel than a traditional switch. That means almost no switching latency, near zero queuing, and the ability to reshape the compute fabric instantly. If a TPU dies, the system cuts it out and reconnects the rest of the mesh. If a customer needs a specific layout for a mixture of experts model or a different geometry for a large transformer, the cluster can be reshaped without moving hardware. And none of this appeared suddenly with Ironwood. Google has been stepping toward this for years. TPU v4 supported pods up to 4,096 chips. TPU v5p doubled that to almost 9,000. TPU v6e refined the fabric further. Ironwood isn't a fresh experiment, it's the continuation of a decade of building hardware, specifically for enormous AI clusters. And that history matters, because Google actually uses these fabrics every day in production. Gemini trains on them, YouTube's recommendation engines run on them. Search ranking runs on them. Google isn't just selling TPU time, it's operating its entire AI infrastructure on this architecture. The clearest sign that Ironwood has crossed a new threshold came from Anthropic. Despite directly competing with Google in the model race, Anthropic recently committed to using as many as 1 million TPUs. You don't hand that level of training workload to hardware you don't fully trust. On top of that, Anthropic is also building huge clusters on Amazon's Trainium 2, which also uses Taurus-based fabrics. That's the moment the industry realized this shift wasn't theoretical. Frontier Labs now see non-Nvidia architectures as viable for model training at scale. For Nvidia, that's the real threat. Not that Ironwood beats Blackwell in flops, but that hyperscalers finally believe they can train frontier models without relying entirely on GPUs. Nvidia's business depends heavily on cloud providers buying enormous quantities of its chips. If Google, Amazon, Microsoft, Meta, and Tesla all continue investing in their own accelerators, Nvidia loses the leverage it has held for more than a decade. Even if Nvidia maintains the most mature software ecosystem, the gravitational pull around their platform weakens. Nvidia still has the stronger software stack, and that advantage doesn't disappear overnight. CUDA, CUDNN, NCCL, Tensor RT, these frameworks form the backbone of modern AI development. But TPU, software, has matured much faster than people outside the research world realize. JAX has become one of the most efficient ways to write large-scale training code. PyTorch XLA is stable enough for real models. Google's compiler work has improved dramatically. And the fact that Anthropic is able to train Claude using hundreds of thousands of TPUs without complaining publicly about kernel issues is proof that the software gap is no longer a deal breaker. But the deeper impact of Ironwood isn't in any one metric. It's in the confidence it gives to the part of the industry that can afford to train extremely large models. It validates the idea that the future of AI compute won't be dominated by a single type of chip or a single vendor. It shows that hyperscalers are now comfortable owning their entire stack, from silicon to networking to model training workflows. It confirms that scalability, topology, and reliability matter just as much as floating point throughput. That's why Ironwood represents a turning point. It finally combines three qualities previous TPU generations never delivered at the same time: competitive chip-level performance, a mature compiler ecosystem, and a fabric that scales far beyond Nvidia's rack-scale designs. When you put those pieces together, it becomes hard to dismiss the possibility that the biggest models of the next decade might not be trained on GPUs at all. The industry is moving toward a multi-architecture future. Nvidia will remain a major player, and GPUs aren't going anywhere, but the monopoly-like position they once held is slipping. Google, Amazon, Microsoft, Meta, and Tesla have all shown they can design hardware tailored to their own needs. Ironwood proves that alternative accelerators are no longer experiments. They are production-ready platforms, capable of training frontier-level models. But while the cloud-level battle escalates, something equally disruptive just happened on the opposite end of the spectrum. Samsung just broke a barrier almost nobody thought was possible this year. A 30 billion parameter model, the kind that normally demands more than 16 gigabytes of memory, now runs on less than 3. Not in a data center, not on a cloud GPU, but directly on a device that fits in your pocket. And the way Samsung pulled this off might reshape the entire direction of on-device AI. This breakthrough isn't a minor optimization or a clever engineering trick. It's a fundamental shift in how large models can exist on consumer hardware. Dr. Myungju Ham, one of the technical leads at Samsung's AI Center, explained how their new compression and quantization pipeline shrinks models by more than 80% while still retaining near cloud-level accuracy. Instead of loading an entire model into memory at once, Samsung's system intelligently streams only the pieces needed at each moment, dramatically reducing storage pressure without degrading performance. But the real magic comes from how Samsung handles precision. Instead of relying on 32-bit floating point math, the company reduces many operations down to 8-bit and even 4-bit integers. Done the wrong way, quantization destroys accuracy. Done Samsung's way, weights are analyzed individually, preserving high precision where it matters and compressing the rest. It works like high-end image compression. The file gets smaller, but the quality barely changes. Compression alone, however, isn't enough to make a 30 billion parameter model fly on mobile hardware. Samsung built a custom AI runtime engine, a kind of control tower that decides in real time which part of the chip handles which calculation. CPU, GPU, and NPU aren't treated as separate components but as a single coordinated system. When one processor hits a bottleneck, another takes over instantly. This dynamic scheduling cuts latency, reduces wasted bandwidth, and keeps responses fluid. The competition should be paying attention. Apple is doubling down on specialized silicon. Google is tied heavily to cloud inference. Samsung is choosing the opposite path: universal, on-device intelligence that runs on almost any hardware configuration. The company believes the next era of AI will be defined not by the size of the model, but by the efficiency you can extract from the device already in your hand. And it doesn't stop at transformers. Samsung is already exploring new architectures designed specifically for real-time, low-memory environments, models built from the ground up, for speed, privacy, and personalization without ever leaving the device. If this scales the way Samsung intends, the boundary between cloud AI and on-device AI may disappear entirely, and the smartphone could become the most powerful AI device people own. So, let me know what you think about these AI chips. And if you want more deep dives like this into the breakthroughs shaping AI, make sure you subscribe and stay tuned. It really helps the channel grow.